Welcome back to Physics 142. We've been talking about circuits and analyzing circuits, and we've recently introduced the idea of Kirchoff's rules for analyzing more complicated circuits. So in this video, I want to do another example of using Kirchoff's rules for a fairly complicated circuit that I've drawn here. This is something called a bridge circuit. And here we have a power supply, but we have a bunch of resistors that are connected in a fairly complicated way. And our goal in this problem is going to be to try to find the current through each of these resistors. So let's go ahead and dive in and see if we can figure out how to find the current through each of these resistors. So just as a reminder, Kirchoff's rules that we're going to be able to use here are one, that we talked about Kirchoff's junction rule, which says that the current that flows into a junction, remember junction is where you have three or more wires come together, so like this is a junction here, that the current that flows into a junction needs to be equal to the current that flows out of the junction. Or if you add up all of the junctions, all of their signs, that should equal 0. The other rule that we have is we have the loop rule that says if we go around any closed loop, so if we start at a spot and end up back where we started, if you add up all of the changes to the potential, to the amount of potential that you have going around that loop, that should sum to 0. All of those potential differences should sum to 0. So to actually solve this problem, we need to label some currents and think about the potential differences that we might encounter. So a good place to start is to put in some currents and then go from there. So step 1, remember, is to draw in currents. Draw in currents. And if we want current through each resistor, well, let's think about the current that will be going through each resistor here. So through resistor 1, well, there's going to be some current. Well, let's think about, so we have current. It's going to flow out of the positive terminal of the battery here. It's going to come along, and then we're going to have some current. Then it splits, right? So whatever current goes through the battery is going to split. We'll have some current that goes through R1. So let's go ahead and put that in here. All right, let's assume a direction, and we'll call that current I1, all right? But then, that current is going to also get split, and some of the current will go through R3 here, so let's draw in a current there, and we'll call that I3, and some of it will go through R4 here, right? And so let's go ahead and draw in that current, right? So here would be a current going through R4, we could call that I4, right? And then over here, well, current going through R2, that's going to be I2, right? And current that goes through R5, well, we should draw that in too, right? That's right here. You'll have different current yet going through R5. We'll call that I5. Now, a couple things to note, all right, is for one, for example, we don't actually know the direction that the current will necessarily be flowing, right? Maybe the current will want to flow through R3 this direction, but we've just chosen a direction, and if we get a minus sign as our final answer, that means that we drew our arrow the wrong direction. So it doesn't really matter what way we initially choose. If we get minuses at the end, then we know we chose the wrong direction. So, all right, so to proceed, first was to use, let's next label any junctions, all right? So let's think about junction rules here. And for a more complex circuit like this, we actually have a few independent junctions that will give us independent information. And the junctions that I want to think about here are it would be nice if we could use junctions to sort of not have to think about a couple of these currents. And so one junction that I might think about is this junction right here on the left, all right? And this junction here has I1 flowing into it, right? But I3 and I4 are both coming out of it. So what I might write is that I could replace I4. One thing that I might just do, all right, is now we want to deal with junctions. All right. Step 2, we'll deal with junctions here. All right. And dealing with the junctions, we want to replace I4. All right. I4 is going to be I1 minus I3. All right. Or said again, I1 is I4 plus I3, right? And so solving that for I4, we get I4 is I1 minus I3. Similarly, this junction over here is going to relate I2, I3, and I5, right? And specifically, I5 is the combination of I2 and I3. So we can write that down. I5 is going to be the combination of I2 and I3. And these give us independent information, so we can have two different equations from the junctions. If we were interested in the current going through the battery, we could also use one of these junctions to do that. We weren't actually asked about that, so I'm not going to bother working out yet one additional current, but we could, if we wanted to, also write down that the current going through the battery is, say, I4 plus I5 or I1 plus I2, right, using one of those junctions there. But for figuring out current through each resistor here, I want to have relationships between the currents that I've drawn, and so these two relationships are a good place to start. All right, so now we've handled junctions. The next thing that we want to do is we want to think about drawing some loops. So I'll draw loops in different colors, all right? We want to use the loop rule here. And so there are a bunch of different loops that we could take here, all right? And so one loop I want us to think about, or one example loop that I'll do, is let's suppose that we start here, all right? We're at 0 potential, and we're going to go a loop around here. We're going to loop around, and we'll go through R1, and we'll go through R4, and then we'll get back to where we started, all right? So this will be our loop, all right? I'll call this loop number 1. Loop 1 here, all right? And for loop 1, now we want to write down an equation that adds up all of the potential changes, all right? So let's now think about loops, all right? And so for loop number 1 here, well, when you go through a battery from negative to positive, right? From the negative to a positive, when you go through battery from negative to positive, you gain potential, right? So we gain positive 24 volts going across the power supply. All right, now we hit resistor 1. And in the last video, I think I mentioned that it's often useful to label the high potential and low potential ends, right? So we could say this is the high potential end and this is the low potential end of the battery. The other way to remember it is that if you go with the current, right? If you go through a resistor with the current, then you're flowing downhill, right? You're going from positive to negative. That means you're going downhill, right? So as long as you're with the current going through a resistor, because resistors are resisting the current, you're going to lose some potential. And so specifically, how much potential are we going to lose? Well, we're going to lose I1 times R1's worth of potential, right? And then here, we're going to lose I4 R4's worth of potential, but I'm going to go ahead and just use this relationship that we wrote for I4 already and say, okay, we're losing I4's worth of current. So I4 is I1 minus I3 and times R4, right? Times R4. And then we're going to get back to where we started. And so if you get back to where you started, all of these potential changes add together should add to 0. All right, so by going around this loop, we gained some potential going across the battery, we lost potential going across R1, and we lost more potential going across R4, and so we write all of those down in this loop. All right, well, we now have 3 different equations, all right, but we had 5 different unknowns, right? I1, I2, I3, I4, and I5, so we're gonna need a total of 5 equations, all right? So that means we need another loop. So let's look for loop 2. So what should we do for loop 2? Well, for loop 2, how about we again start here below the power supply, right? So we're going to start below the power supply, and we'll go along. We'll gain some potential going across that power supply. So we'll again gain 24 volts as we go, as the power supply lifts us uphill, all right? And then, but now, rather than turning and going through R1, let's turn and go the other way, all right? So let's go through R2, all right? And so when we go through R2, we're going to lose some potential, right? We're going with the current through R2, so we lose some potential, minus I2 times R2, all right? And then we're going to go through R5 here, all right? So then we're going to go through R5, and again, we're losing potential because we're going with the current, right? We lose I5 times R5, but I'm going to write I5 in terms of these other currents, I2 plus I3 times R5 equals 0. And I'm just doing this substitution because then we'll only have 3 unknowns with our 3 loop equations at the end. At least that's my goal. So, all right, we have 2 equations with loops, and that gives us a total of 4 equations, but we need one more to deal with all 5 unknowns, all right? So let's go ahead and do one more loop. And we have a couple of options. I could do a loop around here or a loop around here. I'm going to choose... or we could, loop the whole diamond, all right? We have any closed path is a viable loop. I'm going to choose to just do a little loop in the top little triangle of our circuit here, all right? So I'm going to choose to start here around this junction, and we're going to loop down and over and around, all right? So that's going to be the loop we're going to do here. So let's look and see what happens here. So if we start here, and we go across R1 with the current, all right, we're going with the current, then we're going to lose minus I1 times R1's worth of potential, right, going across that one. All right, now going along with the current through R3, when you go with the current through a resistor, you lose potential, so that's minus I3 times R3, all right? And then we need to get back to where we started, but now we're going against the current through a resistor. So if you go against the current through a resistor, well, that's like climbing uphill, right? If you go with the current through the resistor, that's sliding downhill. But if you're going against the current through a resistor, that's like climbing back uphill. So there we're actually going to have plus I2 times R2 because we went backwards through that resistor, right? When you go backwards through the resistor, then you actually add some potential here, all right? And all of these are going to add to 0. So now what we have 5 total equations with 5 unknowns, except I've already substituted in this equation for I4 and this equation for I5. So now what we have here is a system with 3 equations and 3 unknowns. So the next question that we should ask here is, how do we go about solving this algebraically? And I'm going to do that in the next video.